Hey guys, we're going to talk about section 2, effective shear now. I left the Shields diagram here just for reference. So, shear at the bottom of a channel can be simply expressed by these four parameters. The density of water times gravity times the hydraulic radius. This we know is area, or the water perimeter, and the slope of the channel. This will give us units of force per meter squared, and it's a very simplified approach. In general, it provides a rough estimate, which is good. So basically, what I'm gonna try to introduce are these more complex shear stress equations that have been derived for more accuracy in calculating sediment transport. Let's come back here for a little bit. The first condition to use these equations is to meet this constraint. What does this say? It says that the Reynolds number has to be greater than 70. So starting here, we have to get this term right. We know it's it's very hard to calculate, but we can approximate it through this equation. How? Because the friction velocity, U star, equals the square root of the shear stress divided by rho. And what is that? We know this equation. That is just basically the square root of GRH. S. It's just a rough approximation of the friction velocity. After that, we need the roughness of the channel we're talking about. Well, the roughness, as we talk more in the packet, depends on the bed you have. If it's a flat bed or if you have ripples, it's somewhere around this neighborhood, from 10 to 100 times your D50 value of sediment. And then the third parameter is the kinematic viscosity. We know that is basically a constant, just depends on temperature. Now, don't be scared. For most channels, this Reynolds number is greater than 70, which means we can come over here and calculate our shear stress using this fancy equation. So, the total shear stress on a channel, which is basically that over there, is the summation of the effective shear stress plus this double prime shear stress that is created due to pressure on the ripples. So the effective shear stress is basically a local stress that a sediment particle feels in the bed of the channel. For example, here, a particle at this point would experience a skin friction shear stress only, but as we move through the ripples, we have many of those, we also introduce this pressure gradient that also drives sediment into the transport mode. So we have to consider both T prime and T double prime throughout our bed load equations and sediment equations. We're going to use this one a lot, which is the effective shear stress. What is this formula telling us? Well, the effective shear stress is 1/2 times the density of the liquid times 0.06 divided by the logarithm of 12 times the height of the channel divided by 2.5 times D50, this term here squared, times the mean velocity of the channel squared. Okay, fine. Now, as we continue to explore this behavior, we don't really need this second term isolated, so we only present the total shear stress down here as a function of the same parameters we have here. Let's see, 1/2 times density divided by 1.6, 12H. Now here is where we have a change. We have 150. Basically, this term increased to 100 takes into account the form of pressures disruption behavior that we just discussed, and then it gives us a higher total shear stress value, as you will see when you calculate the effective shear stress and the total shear stress. I quickly want to do an example on a channel. We will stick with this channel here for the rest of this video section explanation. Let's calculate the effective shear stress. Let's go ahead and use that. So 1/2 density of water is around 1,000 kilograms per meter cubed, correct? Let's try to do this, times the logarithm of 0.06. Let's hope I can do this. On the bottom, excuse me, I did a mistake here. Density times this 0.06. Let's close brackets. On the bottom, we have the logarithm of 12H. What is the height of this channel? It's 5 meters, so 12 times 5 meters divided by 2.5 times d50. So 2.5. What are the d50 of our particles? It's 0.2 millimeters. Particles are always in millimeters. So 0.2 millimeters is a very small sand particle, almost close to a silt particle. So to make the units work out, we have to multiply times this 2 times 10 to the 4th meters of the d50. Remember to square this term. The velocity of our channel is 2.35 meters per second. We square that, and then we should get a value of 6.42 newtons per meter squared. So this is the effective shear stress. And that would be it for this section.